Okay. So, how was the midterm? Easier this time, right? What's that?
Not good result for us and for you.
Yeah. Well, I think it was. It was.
How quick you was?
What's that?
How quick?
Oh, it depends on my availability and how willing I am to grade.
Actually, we didn't got any email. I just randomly checked and I found one. I think the chain goes like this.
Well, but I still couldn't write down the solutions manual, and I couldn't gather the statistics. But I'll let you know as soon as possible.
You got our homework results yet?
Yes. Well, now, as for the homeworks, I need to give them to the assistants. And no, I do have time. But the point is, they're not experts in this field. And they cannot write solutions manual on their own. So I need to write down the solutions manual for them, and that's the bottleneck. So, but don't worry about them. Okay, I'll try to speed it up.
So our projects are going to be graded after our presentation?
Yes, so it's going to be some sort of average of your presentation and the paper. I haven't decided on the distribution yet, but yeah, it's going to be some.
I have a question. You told us about 5 pages and 5 pages.
Did I? Okay.
I don't know, but my answer was so confident.
Mm-hmm.
I barely fit it in about 10 pages.
That's too long.
What?
That's too long.
Too long?
Yeah. So, well, there's a page limit for a reason. And the reason is I wanted you to read the subject, really understand it, and compact the information in such a way that you can demonstrate your ability that you can understand and write things down in your own words.
But you also said it must be, I expect that
Mm-hmm.
it is 3,000 words.
Yes.
In 5 pages is about 1,000 words.
No. Well, I think there's a calculation. Well, 3,000 verses is the actual. I cannot remember why I said 5 pages, but 3,000 words is the limit. It's a typical limit for journals. It's a very typical limit you will find in many journals, and it's typically 5 pages long. I mean, you can make the font smaller and
Yes, of course,
Yeah.
I was thinking about that, but I said, if I decrease the font, it
Mhm.
will be fast.
no. Then you have too many words, because you can clearly read many journals, right? And they have a limit of 3,000 words. It's fine if it is like 3,500, but I don't know what to do with 10,000 words. Okay. So for the presentations, it's going to be 15 minutes in total. I think it's better to have something like 13 plus 2 or 12 plus 3. So you present for 12, 13 minutes and then leave room for questions. Okay. And for the presentation, make sure that it's, I mean, all the people here has a certain level of knowledge about the topics. So don't go into extreme details. Try to start from a level so that everyone can understand, but it's not going to be like you're trying to explain things to an to a person who has no idea about what we are doing here, okay? So it has a certain level. Okay, do you guys have any questions? So I think we will start presentations next week, Tuesday. So we'll have only 2 days for that. We have total 3 hours. So I think the time should be sufficient. We have 180 minutes in total. No, we don't have 180, we have 150 minutes. And if everything goes according to the plan, we have 9 people. So it's going to be 135 minutes, so we'll have 15 minutes extra for switching in between. Or we can use some of the spare hour we have on Friday, we'll see. But we'll do it next week. And we'll do it in a random order. So be prepared. I'll announce it beforehand, but I'll write a random number generator and list you in a random order for the presentations. But I'll announce it probably sometime before Friday.
Maybe we can follow that order.
What's that?
We can follow that order. We have order list.
Well, what's that?
We start first. Okay, we'll start first.
Okay. We'll see. All right. So last time, this is, I guess, what we have done. Nope, not this one. This one. So we started with superconductivity, and basically the idea in superconductivity was for certain materials, as you lower the temperature, what happens is that at a certain critical temperature, resistivity of the material drops down to 0. And as we mentioned, this is not just some decrease in resistivity, it is true 0 resistance to the flow of electric current. And we have seen actually in the periodic table, almost all of the non-magnetic materials display such property, superconductivity, and here are a list of some of them. And then there are some other superconducting materials that are in the compound forms, and they can display very high superconductivities. One of the very famous example is YbCO, yttrium barium copper oxide, which shows superconductivity at 90 Kelvin. That's particularly important because it's above 77 Kelvin, which is the point of temperature of liquid nitrogen. So boiling point of liquid nitrogen. So it's above that temperature. It's very easy to achieve 90 Kelvin. And then we discussed Meissner effect, which is expulsion of magnetic field. And then we looked at classification of superconductors. We said there are classification based on the effect of magnetic field. For instance, type 1 is there's a single critical magnetic field that destroys the superconductivity. So as you increase the magnetic field on a superconducting material at a certain critical magnetic field, superconducting order is destroyed altogether. And in the case of type 2, there's a range of magnetic field that gradually destroys the superconducting order. So you start creating islands of superconducting regions, and then in between you have normal conductor, and then the change is gradual. And for such superconductors, actually the change, the TC, is also not as dramatic as type 1 superconductors. So there are also classifications based on the theory of applicability. if you can apply the BCS theory, we name it the conventional superconductors. If you cannot, then we name it unconventional superconductors. Also, according to the critical temperature, we say high TC if it is, the convention is if it is above liquid nitrogen temperature, or low TC if it is below. And I think all the high TC superconductors belongs to type 2, but not the opposite is not true. You can find low TC superconductors that belongs to group type 2. Okay? And we started discussing the BCS theory. So the name comes from these three physicists, Bardeen, Cooper, and Schrieffer, and from this 1957 paper. Then the idea here was there's an attractive interaction between the electrons, and that attractive interaction comes from the fact that electrons interact with the lattice, and then they distort the lattice. So here's the drawing. An electron distorts the lattice, and then another electron from a far region can feel the effect of this distortion, and this new energy minimum is an attractive point for it. So it will form a bound state with the other electron in the system. So below that critical temperature, because of this lattice distortion, electrons start acting together. They form a pair, and this pair is typically called the Cooper pairs. And this pair, formed of one spin up, one spin down electron, starts acting as a boson, which these quasi-particles can occupy the same quantum state, regardless of how many other quasi-particles in that quantum state. So all of a sudden, within this piece of material, all these electron pairs start having the same wave function. You can describe them with the same quantum state. And this means that this is now in a superfluid phase, and the coherence length goes up to hundreds of nanometers, and the microscopic details, by microscopic details I mean really like atomic details, defects and other stuff, cannot change the state of these quasi-particles. They will not be affected by any such impurities, and then they start showing this electrical conductance without any resistance. Then we discussed London penetration length, which was a length that shows how deep a magnetic field can penetrate into a superconductor, and it is given by such an expression. Then for case of aluminum, it was only like 0.16 nanometers, which is extremely shallow. But this penetration plays an important role in some of the unique features that we observe in superconducting materials, like magnetic levitation. So when you place a piece of magnet over a superconductor, or it can be the opposite, you can place a superconductor over a magnet. Because of this penetration, the magnetic field creates eddy currents within the superconductor, which can go in loops without any resistance. So they are permanent currents that are created by the magnetic field. And these permanent currents create their own magnetic field, in a way the mirror image of the magnet that you put on top of the superconductor or below the superconductor. So this image magnet now can keep stable, or it can levitate, and it can overcome the force of gravity because of this magnetic repulsion between between these two, real magnet and the image magnet. You have a question?
Is this the same reason that when we drop a magnet inside the copper pipe, it slows down?
Well, the idea is similar. In the copper pipe, when you drop a magnet, as it travels through, because of the magnetic field, it creates eddy currents, which opposes the magnetic field of, so it creates a force, and that force can resist the gravity. But copper is a lossy material, so you cannot create these superconducting currents. But in this case, you can create superconducting currents, which can create equal force to carry the weight. So the idea is very similar, but the mechanisms are, I should say, different, or the reason, well, they're similar. Okay. They have the same physical reason in very basics. Okay, so we also discussed how you can measure zero electrical resistance, and the idea was to have this 4-wire configuration. And now I'd like to continue with the BCS theory and try to give you a little bit more details about the BCS theory, its applicability, and then we'll start discussing the Josephson effect, which is an important I don't want to say application, but some sort of application of superconducting materials. So let's continue with BCS theory. It's mostly applicable to type 1 superconductors. And as we have discussed earlier, the idea is that copper pairs form, you can see it, right? You can read it. Copper pairs form through interaction with the crystal lattice. Okay, and as we have discussed, these let me use red. These electrons interact via this phonon interaction, okay? So they don't talk to each other directly, but there is a phonon interaction, and the range of this interaction is on the order of hundreds of nanometers. And if you compare this to lattice spacing of a crystal, which is like 0.1 to 0.4 nanometers, that's a massive length. It's almost up to 1,000 unit cells of the host material. And one of the outcomes of the BCS theory is that it says if we have such a protected state, then there must be a band gap separating charge carriers from the state of normal conduction. So what it says is you have normal conductors at the Fermi level, Fermi surface, and then in the superconducting space, we should have a band gap. So my superconducting states will be about this band gap, and my normal carriers will be isolated from the superconducting state. So there will be no interaction between the normal conductors. So this band gap will also protect these states from, for instance, thermal fluctuations. And one of the proofs is actually this. Let me show you this experimental evidence. Let me see if I can find that picture. Yeah, this one. So let me increase it a little bit. So this is the specific heat for vanadium, okay? And specific heat is given by basically the change of internal energy with temperature, okay? Now, what they do in this experiment, let me see if I have the citation. I don't have the citation, but what they do is they apply a certain magnetic field to vanadium, and vanadium stays in its normal state. So this is T square. So this is where 5.4 Kelvin is. And it stays in normal state. And this is the heat capacity of vanadium when it's in normal state. Temperature dependence, I guess, goes with, so C scales with T, okay? So it doesn't change with the temperature. Oh, sorry, it decreases with the decreasing temperature. And, but in the superconducting state, it follows the same trend, okay, up here at higher temperatures. And then it goes into an exponential regime. And the idea is, actually this is one of the early suggestions that there must be an energy gap in the superconducting state, this exponential dependence of the heat capacity, because the idea is roughly as such. Imagine we have a two-state system with one of the states is at energy delta E and the other state is at energy 0. And the idea is we would like to take some population from this 0 state to delta E state. But since this is a quantum mechanical system, I have to exactly provide this much energy into the system. So also there will be a temperature distribution since we are dealing with this material at finite temperatures. So the idea is that any such transfer will be exponentially suppressed with the temperature. So if the thermal energy, kBT, is much smaller than the separation delta E, then the probability of taking any population from here to here will be exponentially suppressed. And actually BCS theory explains this very well. I'm not going to go into the details of the calculation, but the heat capacity follows such a trend. So you have the heat cap specific heat, some C0, and then B over kBT. And it turns out that this B is half of the gap. So it's delta E over 2. And this is a very common trend we see in quantum systems or even superconducting systems. Whenever you have an energy gap, the charge transfer from one state to another is, it follows such a relation which is called yes, Arrhenius type of relation. We have seen exactly same thing in semiconductors, right? The electrical, oops. resistivity versus temperature would follow such an exponential trend as you decrease because of the exact same reason. So to be able to have some charge carriers across the band gap, you need to transfer some population from here to there, and it requires this thermally activated behavior. So the higher the temperature you have, the more charges you will have here. So the heat capacity follows a very similar trend in that sense. And according to the BCS theory, this is what you get. And it is roughly equal to this number. Gamma here is actually a bunch of constants. Rho f divided by 3. And rho f is the density of states at the Fermi level per spin. And if you really measure the specific heats, or I should say this change in the specific heat, so this is delta C, for many type 1 superconductors, you will see that they exactly follow such a trend. So this is one of the successes of the BCS theory. It can explain the formation of the energy gap, and also it can predict why we have such a behavior of this specific heat for materials. Then another success is that after some lengthy algebra, what you need to do is actually solve the Schrödinger equation for two electrons as well as their interaction with the crystal. And once you do this, you can write down the findings of the BCS theory. And one of the other finding is that this energy gap follows such a relation. So delta E divided by KB Tc, this is the critical temperature for the superconducting transition, is equal to 1.76. And let me see if I have that. By the way, this is a very nice website for basic understanding of many physics concepts. It's hyperphysics. If you already don't know, it's simple. It's just for basic understanding. But if you want to remind some stuff to yourself, it's a good visit. Yeah. So this graph, I hope you can see it. Let me expand it. This graph shows the measured band gap versus the predicted band gap, or T/2 KTC, which is the same thing as what I've written, and it follows a very nice linear trend. Of course, there are some deviations. Well, I'm not sure why, to be honest, but it's the others are pretty in line. I'm not sure why lead and niobium and mercury are slightly different. Okay. All right. So what do you mean, like an ideal? Yes. Now, but now the idea here is that these impurities really do not affect the superconducting order. And when they do start affecting, it starts destroying the order altogether. So this is really the coherence length of Cooper pairs are so large that any such defects and impurities they don't want. And as we'll see in Josephson effect, even if you like insert an insulating material in between two superconductors, the superconducting order doesn't bother by such insulator in between the superconductors. Yes, please.
You made an assumption that KZ is much smaller than delta E.
No. It wasn't an assumption. This was, in this case, there will be no charge transfer from the zero ground state to the excited delta E state. That's what I meant. This is not an assumption. As you get closer to this energy, delta E, this thermal energy, actually this becomes very close to here. Okay, it's not an assumption. Okay, any other questions? Okay, now let's go to the Josephson effect. Let's say I have a superconductor here, and then in between I have a non-superconducting material. And this non-superconducting material can be an insulator or it can be a normal metal. And on the other side, I have another superconductor. Now, in the case of insulator, to be able to see the Josephson effect, you need something like, I mean, it doesn't have to be 2 nanometers, but give or take something like 2 nanometers. For a normal metal, you can go up to tens of nanometers and perhaps even larger than that. Okay? So the question here is, I have copper pairs on this side, and I have a tunneling barrier here. So the idea is how these pairs will tunnel across this junction. What kind of IV characteristics will I see? Okay. Now, this effect, let me write this down, in essence describes tunneling of copper pairs through a non-superconducting junction. Okay. Now let's try to find out how it will work. So let me label this side as A and this side as B. Okay? And I'm going to write down the Schrödinger's equation for both sides. Okay? So where do I have that? Okay. So I have IH bar, okay, del by del T phi A. So this is the wave function on this side. And then what I have is minus H bar T phi psi B. Okay, and this guy is the electron pair coupling or transfer interaction across the junction. So what it relates is, it relates the rate of change of the wave function on the A side to the B side, since this is what I have. And I can write the opposite, so I h bar del phi b by del t, so rate of change of wave function on the B side to the A side with the same interaction. So I have two equations that are coupled to each other. So also I have phi n and phi psi a psi b that are coupled to each other. So I can solve these two equations together to find the relation between probability amplitude transfer from one side to the other. Now, one other thing that I need to write down is the wave function for the pairs on either side. And it turns out the wave function is square root of NA I theta A. So this is density of Cooper pairs, and this is some phase factor. Okay. So we treat them as sort of plane waves, and the way to derive this, actually, once you solve the Schrödinger equation for such Cooper pairs, BCS theory gives you such a wave function. And also for, let's write the exact same thing for the B side. So I have these wave functions, what they look like for both sides. So all I have to do is plug in these wave functions into these equations and find an expression for density of Cooper pairs and these T and other stuff. Okay, so first, perhaps I should also say this HT measures how much this leads to this. So what we are looking at here is, as we mentioned before, is a tunneling event. I have a plane wave of Cooper pairs, okay, described by such a wave function, and there will be a tunneling event, and some of them will be leaked to the other side. So I'm trying to find a coupled equation that will describe the mechanics of this thing. So let's plug in these wave functions into the expressions, and what I get is something like this. E to the I theta A del NA del T plus I psi A theta A del T minus I T psi B. And then for this expression, I have 1/2 NB minus 1/2 e to the I theta B del NB del T plus I psi B del theta B. Sorry, I made a mistake here. This is equal to this. Okay. Because I write this down, so I canceled H bars on both sides, and I moved I to the other side, it gained a minus sign. Del T equals to minus IT psi A. Okay, so it's one of the equations. This is another equation. Basically, this one is this equation, this one is this equation, just evaluated the integrals. Okay. And if I multiply this by square root of NA e to the minus I theta, I multiply both sides, and this one by such an expression, then what I get is this. 1/2 del NA del T plus I NA to IT NA NB minus 1/2, sorry, plus e to the I theta A minus theta B. Then same thing here, just I replace A's with B's, 1/2 e to the I, this time with a minus sign. Sorry, this one is B, this one is A, B. Theta A. Okay. Then there's, now I can I have similar expressions all over the place. So what I can do is I can equate these two. So I'll get such an expression, 2t square root of NA NB sine theta B minus theta A. Okay, so I started with the wave functions, and from there I have written an expression in terms of densities and the phase and this T transfer. I don't want to say energy because it's transfer weight. So it's a more compact expression. And I can write a similar thing for this guy as well. There's minus 2t NA NB sine theta B minus theta A. And also I can write an expression for the phases. Okay, minus t NB over NA 1/2, this time cosine theta B theta A. And similarly for this guy, I have such an expression, positive cosine theta B theta A. Now I have 4 equations, and then I can solve for these expressions. Now I kept it general. I assumed that NA and NB are going to be different. So if you take 2 different superconductors, for instance across the junction, then you'll have different densities. But for identical superconductors, NA is going to be roughly equal to NB, unless you're in the extreme cases like very large biases and so on. So this is for identical superconductors on both sides. Then these expressions will be reduced down to this. So the rate of change of phases across the junction will be the same, and indeed this guy is going to be 0. So the rate of change of the difference between these 2 phases will be identical. Also, the change in B will be the negative of change in A, which makes perfect sense because I transfer some population from side A to side B. Okay? Now, okay. Let me see. So there's one more thing left to write down. Let's do it after the break. So I'll show you what is really Josephson effect and how we derive it. Okay.
is not impossible. There is a continuous progress.
Okay, so we ended up with these equations. There's one last thing that I'd like to show. So we can derive a relation for the current that goes through this junction. We can write down an expression for the vector current in terms of the wave functions, transfer of wave functions, and that expression would read something like this: IQH divided by 4m, and then okay, and minus again q squared over 2m a times wave functions. And here q is minus 2e, since we are dealing with this quasi-particle that has 2 electrons in it, and m is 1 electron's mass, but as you can see we have 4m and 2m. Actually they are sort of doubled. Okay, and if you plug in these expressions from these wave functions into this expression, you end up with such a vector current h bar en over 2m. Then you take divergence of the phase, and then e squared n over 2m and the vector potential. Okay, this is a very general expression, by the way. Okay, for any quantum current that goes from one side to another, you can write down such an expression. And if you remember, we discussed this when we discussed the Landau quantization. I can make such a gauge transformation, okay, and also I can go from something like this, and this will simplify the overall expression. Okay, so I can let me keep this aside. So this gauge transformation, okay, that I can make to simplify this expression. And if now, in my case, there's no magnetic field, so I don't have to bother with this. But as I'm going to show you in a minute, I can write the current that goes through this junction as such based on this equation. I0 sine theta b minus theta e. I'm going to show you where this comes from in a minute. So what does this tell us? Well, this is some maximum critical current, and then depending on the phases in superconductor B and superconductor A, there's a sine function that modulates the amount of current. Okay, so indeed, through a Josephson junction, if you apply a current and measure the voltage drop across the junction, this is sort of what you get. Now, let me draw this guiding line first. Okay. So let's start from negative biases. You get a pretty linear behavior. And then at some point, voltage drops to 0. And then you still have current flowing through the device, although the voltage across the junction is 0. there is from minus I0 to plus I0, there's a flow of current. And then once you reach I0, you again have this V0 bias that appears across the junction. Yes?
Is it behaving like a superconductor in that region?
Well, it's always behaving like a superconductor, but we have two superconductors. But yes, in a way you are right. And then we have two superconductors, and then in between I have an insulator, which ideally should act as a barrier. So if I had two normal metals that are connected together with an insulating region, I would see a very small tunneling current. And then once I increase beyond that barrier energy, I would observe a very dramatic increase in the tunneling current. So when I change the bias though, the voltage difference would increase and increase with minimal current flowing. But in this case, even if I apply 0 volt bias, the electrons keep tunneling. That's the difference in between normal tunneling and the superconducting tunneling. Okay? So the picture here is a little bit inverted. We are so used to the idea that I apply voltage bias and then I measure the current that flows. Here I apply current and I measure the voltage drop across the junction. But what I see is, although I have a finite current flowing within a range, okay, the voltage drop across the junction is 0. This means my superconducting parts are behaving as a single piece. This is what you would get in a single piece of superconductor, right? This was the idea. This is how we measure superconducting persistent currents in superconductors. There are currents flowing through. Since there's no resistance, there's no voltage drop. So the same idea applies within this region. Okay, so this is one of the interesting properties of such a Josephson junction. Cooper pairs tunnel through without any need for a bias. Okay, so this is called the DC Josephson effect. Okay, and let me check if there are any other things that I need to mention regarding the DC Josephson effect. Well, now let me go to AC Josephson effect, and yes, please.
So, for example, you know that the Cooper the act like ozone score.
Yes.
So when you tunnel it, so this levels of that insulator, I think they act as a homogeneous rather than ozone square. I think it's a difference.
Yes, I mean, you can have a normal metal or an insulator.
So, but there's no interaction between them, they just can't.
Well, okay, if you really want to know the mechanics, like how these Cooper pairs really tunnel through such a barrier, I don't want to say something wrong because I'm really not an expert in superconductivity, but as far as I know, what happens is that right at these points, well, I really don't want to say something wrong, so I don't think, well, they don't live, first of all, within this material. Okay, they don't enter into the insulating regime. So I think it really doesn't matter what kind of, since they don't enter, we cannot say whether they will behave like fermions or bosons. So The part that I didn't want to comment on is, now let's say I have a Cooper pair approaching to this barrier, okay? Now, what is the tunneling mechanism? Like, what happens right before the interface? Do I break that Cooper pair and electrons tunnel one by one and form new pairs on the other side? Or these pairs tunnel together and they continue their journey there? That, I don't know.
This is for electron, not for the boson. I don't know. I also don't know that.
Mm-hmm.
I mean, sort of explain at zero voltage.
Mm-hmm.
For example, we have this boson passing in because there is no interaction with the fermion in the system. I don't know, but that's my.
Well, yeah, there are no, actually one of the basic findings of the BCS theory is that you have no fermions remaining in the superconductor that contributes to the conduction. Okay? They're separated by this gap, and none of the fermions now contribute to the conduction. So we shouldn't think about fermions going from one side to the other, but then I really don't know about the mechanism right before the tunneling. So I really don't want to say embarrassing things on that.
Interesting.
Yes, yes, it is very interesting. But now let's move on to AC Josephson effect, and that's even more interesting. Now, let's apply some bias across the junction. Okay. So this is something that I can do since now I have a normal conductor and then a superconductor and then insulating barrier and then superconductor and then a normal conductor, okay? So I can apply a certain bias across these. Yes, there will be, let's say I applied V here, there will be minus EV on this side plus EV on the other side, and these guys will be in equipotential, okay? So in this case, I'm trying to measure, I apply a voltage across the leads. So this is my side A, this is my side B. Now, the equation that I have written about is going to be something like this now. I have on one side now I have this new term, and for the other wave function I'm going to have h bar t psi A plus EV psi B. So I have two new terms because of the potential difference in these Cooper pairs within the superconductor. Again, this is not a difference between within the superconductor. This is a difference among the superconductors. Okay. Now, what I'm after is the current that will run across this junction because of this bias. So this time I'm going to skip the algebra. What I'll get is something like this. The phase difference, theta B minus theta A, will now be given by such an expression. Now let me label this as delta with some difference. So del by del t, this is a function of time, is this. So if I solve this simple differential equation, this is what I'm going to get. 2 EV over h bar t. So this is the phase difference between two sides before I apply the bias. And this is the phase difference at any time t. And it's a function of the potential difference across the junction. And there's this factor of 2e, because any voltage that I apply on these pairs will have 2 eV energy difference divided by h bar times t. Okay, this will give me the phase difference. Now, if I plug this expression into this continuity equation that I have written here, okay, this expression, this is what I get. I0 sine delta 0 minus 2 EV h bar t. Okay. So now I have a new expression for the current that runs across the barrier. Okay. And this is called the AC Josephson effect. Now, the naming is very bizarre. DC Josephson effect, you basically don't apply any bias. So it's both superconductors are at the same voltage, but you still have this current flowing between these two superconductors. In the AC Josephson effect, you apply a DC bias, and then you get this oscillatory behavior for the current in time. And the interesting thing is that if you apply 1 microvolt across the junction, then if you plug in the numbers, you will see that this corresponds to 483.6 megahertz oscillation in the current across the junction. Okay, so if you apply 1 microvolt and try to measure the current that flows across the junction, you will see that it goes up and down between this I0 value, 483.6 million times a second. It is measurable. It's not too crazy. I mean, it's doable and people measure it. Actually, AC Josephson junctions, it's a so long name, so I'll say ACJJs, are used as voltage standards. So what they do is they put multiple Josephson junctions in series. By multiple, I think something on the order of 100,000s. I don't really know the exact number, but something like tens of thousands at least. And by doing that, they can create more sensible voltage differences. They can bring this up to 1 volt. And we can measure time very precisely using atomic clocks, cesium clocks. Okay. So we have a standard for time. We can precisely measure time. And using this time measurement and these Josephson junction arrays, we can define what 1 volt is with an error of 10 to the 9, 1 part in 10 to the 9. So we can precisely measure or create a voltage standard using just Josephson junction arrays. Now, there's a video that I'd like to show you. It briefly, I mean, it's a very old video, but the idea is there. It briefly describes how they achieve these Josephson junction arrays, and also they demonstrate the DC Josephson effect. So let me play this video. So there's this superconductor and insulator, and actually, yeah, this is the structure that they fabricate. So they have superconductor, insulator, and superconductor on top. And using focused ion beam etching, we have one downstairs, they open up sites like this. They use gallium ions to bombard these regions, and they open up. Yes, Mike? Yes, so they evaporate first layer of superconductor and then evaporate an insulator on top. No, I'll show you the compound. Let me see. It's something like this. It's, what is this? Titanium, barium, calcium, copper oxide. It's an alloy. It's a high TC superconductor. Okay, so what they do is they evaporate first layer, and then on top they evaporate the insulator, and on top they evaporate the another superconducting layer. And I think somewhere here they have gold contacts. I think it comes like this. Then using focused ion beam, using gallium ions, they etch these regions. Then they continue etching. You can see this region, so they etch it at an oblique angle. They etch, so they form a bridge from this side. And then they etch the top superconductor. Okay, so what they end up with, okay, I think they show it here. Let me stop the video. Let me pause the video. So what you have is a superconductor. So metal junction is here, insulator, and then another superconductor here. So you have SIS junction, and this will act as a Josephson tunneling junction. Okay. Then they load it. So this is the chip that contains the Josephson junction, and they have electrical connection. And then they have this outer shield that has these windings around it. This is a solenoid, and they use the solenoid to counteract the Earth's magnetic field, because even the Earth's magnetic field is strong enough to destroy the superconducting, not the superconducting order, but modify the tunneling in these Josephson junctions. Okay. And they insert it into a, I think, liquid helium dewar. So they insert this rod into a bath of liquid helium within this dewar. And then, now what you see here, this is the IV measurement that I showed you. It's sideways now. This axis is the voltage. This is the current. Okay. And they slowly change the current on the solenoid, and we'll see why we have these oscillations as well, but they, by slowly changing the current, they maximize I0 here. We'll see, it goes 0 again, and then now it will have a maximum. Now this is the point where they exactly counteract the Earth's magnetic field. So they have a current flow without voltage. This is what you see in that graph. Okay. And so this is the material as I showed you. Okay, I think that's enough for that. Okay. Of course, there are more details in Josephson effect. I mean, it's who had the Josephson effect? Yeah, you had. So, do you have anything to add? Okay. So, there are many other things. Like you can couple this to an RF source, and you can demonstrate these AC Josephson steps but I'll leave it to Sohail. Okay. Now, one other thing that I would like to discuss is macroscopic quantum interference. Now let's say I have such a material okay, and here I have my Josephson junctions. Okay, so these are superconducting materials, and this black region is superconductor, and these blue regions are my insulators, and I have two paths. So the total current that goes through the main arm is I total, and then I have arm A and arm B. Now, what I have here is I apply a magnetic field through this device. So the phase difference across the junction, here let's denote it, I mean this is going to be a little bit confusing, I'm sorry for my notation, but okay, let me remove this confusion by doing this change. Let me label this as arm 2, and this as arm 1. And so the phase difference here is going to be 1 and 2. Okay, so this is the exact same thing as this guy. Okay, since I have two junctions here now, I need to distinguish them. So when there's no voltage applied, if you remember from the Aharonov-Bohm effect, the difference between these two arms is going to be given by such an expression. So this is the flux, magnetic flux. Okay. This is the quantum of magnetic fields, 1 over quantum of magnetic flux, and this will be the phase difference between the two arms of this device. Now, I can write such an expression. B is going to be delta 0 plus E over H bar flux, and A is 0 minus E over H bar phi. So this and this, there are zero field phase difference. Okay, so it's going to be the same for both cases since there's nothing to break the symmetry of these junctions. And what I do is that this must be the total phase difference. So half of the phase difference will, half of the current will advance by, sorry, again, I'm sorry, I need to fix this. So this is 1, this is 2. So half of the phase will be retarded by this much, and the other half will be advanced by that much. So we'll have the total change in the phase accounted at this output current. So if I plug in these expressions to the expression that I derived earlier, this is what I'm going to get. I total is equal to I0 times sine delta 0 E over H bar times phi plus sine del 0 minus e over h bar pi. And this can be written as 2i0 sine del 0 times cosine e phi over h bar. Okay, so the total current that will be coming out of this device depends on the magnetic field that I applied. But this dependence is in this cosine term. So what happens is that, so let me draw this. This is the total current, and this is the applied external magnetic field. So this is 0, and this is in milligauss. Okay, it is 10 to the minus 7 Tesla. Okay, it's an extremely small magnetic field. As you know, Earth's magnetic field is about a Gauss, so we are talking about an extremely small magnetic field. So what you see is this. Of course, it has a well-defined period, okay? And this period basically corresponds to this. E phi over h bar is some s, this is an integer, times pi. So every time this reaches to an integer multiple of pi, I observe a maximum because this cosine, this term, this gives me 1. So I observe a maximum. And every time I'm pi over 2 shifted by that, I observe a minimum because of distractive interference of electrons that are phase shifted by this magnetic field. So what happens, let me explain it more explicitly. I have a wave traveling here and another wave that's traveling here. When there's no magnetic field, they have the exact same phase. Maximum for maximum, minimum for minimum. So when they reach at this point, both of them have traveled the same path. So they will always be in constructive interference. When I start tuning the magnetic field on, depending on the strength of the magnetic field, one of them will be shifted. Of course, both of them will be shifted. One of them will be advanced, the other will be retarded. And depending on how much relatively they advanced or retarded with respect to each other, at this point I may see a destructive interference. Okay? And this destructive interference results in a decrease in the current. Okay? And it is extremely sensitive. This device is called superconducting quantum interference device. There's a U in between, and there's no C here. So people say it's squid. Okay? So this is added, this is removed. Superconducting quantum interference device. And this device has a sensitivity of 10 to the minus 14 Tesla. This is a crazy low magnetic field. When your heart beats, because of your turning on and off the current constantly, it creates 10 to the minus 10 Tesla magnetic field. That's an amazingly low magnetic field, by the way. And your brain, it's a very intricate, complicated wires, and one current going in one direction, another one going in the other direction. So these magnetic fields cancel each other, but still it's 10 to the minus 13 Tesla. And there's a certain magnetic field.
How could they measure that much?
SQUID, superconducting quantum interference device. If you can bring one close enough to your brain, and of course cancel out the Earth's magnetic field and so on, you can measure the brain's, the magnetic field created by a brain. Yes, please.
Is this how they make brainwaves?
No, I think they use electrical methods because it's much easier to detect. But in principle, you can use squids. The main difficulty here is that you need a superconducting device that is operating at some like 100 degrees lower than the room temperature, and it needs to be brought very near to a machine that operates at 36 Celsius. So it's very difficult to maintain the superconducting state. So, and also, I mean, now this is like an industrial device. It's no longer a device that is specifically used for research purposes. You can go and purchase superconducting quantum interference devices, and you can purchase ones that are attached to atomic force microscope tips or STM tips. So you can approach to a surface with a superconducting quantum interference device and scan the surface with such a device. So it's no longer just for research purposes only. And there are lots of variations of superconducting quantum interference devices. People use them to detect that there's something called quantum gyroscope. They can measure rotation of an object with extreme precision. They attach superconducting quantum interference devices on top of missiles. So when they travel, I was extremely surprised to hear that when in University of Washington there's a group that uses superconducting quantum interference devices to detect dark matter. And one of the outcomes of their research turned out to be they used these extremely sensitive devices that they manufactured in missiles. So what happens is that Earth doesn't have a uniform magnetic field. It varies from place to place. For instance, if you have a very large iron deposit in a certain region, the magnetic field is very different. So the magnetic field landscape is very rough. If you want to send a missile from point A to point B, of course, this A and B is separated by hundreds of kilometers with a precision of a few meters. So you send this missile and you want to hit your target within a few meter precision, let's say plus minus 5 meters precision, then you need to adjust the course of this missile while you travel across this path. And magnetic field is one of the influencers of the trajectory of the missile. So what they do is with these superconducting quantum interference devices, they measure magnetic field variations in real time, and I'm talking about tiny variations, and they adjust the course of the missile in such a way that they can follow the desired trajectory. They do a similar thing with another device that measures the Earth's gravitational constant, or the acceleration constant. Then they again adjust the missile's trajectory using these. So with these two information, they can hit a target. I think plus minus 5 is too much. It's like plus minus 1 meters. No. This is like extremely, extremely precise. And this happens extremely fast. It's much more precise than GPS. Okay? And in GPS, there is a latency. You have to send, the information has to arrive, processed, and sent back. So a few seconds later, take the information, process, send back. So there's a latency. And this happens very rapidly. You know, they travel at Mach 4 or much, much higher speeds. So what you need to do is you need to adjust the course on board. And what happens if someone cuts off the satellite? Okay, now this is going into a discussion of how to build a functional missile. But what I'm trying to explain is, of course, don't go and make missiles. But such research, like the Josephson, this is a crazy guy actually. He got the Nobel Prize for the discovery of Josephson effect, and then have you ever seen his picture? And then he, until quite recently, this is the guy. This is Josephson. He had a brain research institute. He was a physicist, but he's a little gun crazy, and he was doing really odd stuff about brain research. It was, of course, all theoretical, but whatever. So what I want to say is that what this guy discovered a long time ago seemingly had no applications, all of a sudden turned into something that has very large, big implications that can be used from, I don't know, brain research to, I don't know, killing people. So your discoveries may affect 1960s. I mean, the discovery is 1960 something. The guy is very old. It's just trying to translate, understand in Turkish. Sorry, it's, I mean, I'm really interested in lives of such people, and because they're like, yeah, he's born in 1940, so he's not that old. He's old, but not that old. Yeah, he's still alive, yes, and he's still at, I guess, Oxford or Cambridge. I cannot remember. Cambridge. Yep. I've read, I think. Yeah, so this part. Josephson's reputation for promoting unorthodox causes was cemented by his support for the ideas of water memory, cold fusion, so on. Whatever. So this is the guy. So do you guys have any questions? I think this is it for what I prepared for today. I think we are done pretty much with superconductivity. I mean, of course, there are many other things that we can discuss about superconductivity, but these are the basics of superconductivity that I think that every scientist should know about. You guys have any questions? All right, yeah. Yes, I'll upload them very soon. Okay. All right, so see you guys on Friday.